All right, this video is called Potential Energy Diagrams. You're going to be looking at two different pages of notes. You should already have copied down from Schoology. Potential Energy Diagrams. Our state standard is P.10.1. And then you have some basic information about potential energy diagrams. And then you also have 3 diagrams, and we're going to look through those today. You have to be able to label them. Okay, so let's look at our 4 questions we should be able to answer today. What is the energy of a reaction? How are endothermic and exothermic reactions different? What must happen in order for a reaction to begin? And how does a catalyst impact the energy diagram? So we're going to be able to answer all 4 of those. We have the notes here, and I've just kind of rewritten them in a way that's easier to read from the video. Okay, so we'll slide this under so we can refer back to our questions. All right, let's look at potential energy diagrams. First of all, we have to understand what happens in a chemical reaction. In a chemical reaction, energy is either going to be absorbed or released. And we've talked about that many times. If energy is absorbed, it becomes what we call endothermic. If energy is released, then that reaction is exothermic because energy is exiting the reaction. So absorbing is entering the reaction, and releasing is exiting the reaction. So absorbed is endothermic, released is exothermic. Okay, so what does that mean? Well, that's looking at the product energy and the reactant energy. If the product energy is higher than the reactant energy, then the energy was absorbed, and we can see that here. So if the product energy is higher than the reactant energy, energy was absorbed over the course of the reaction. So if I subtract products minus reactants, I'll get a positive number, and we call that the heat of the reaction, or the delta H. So a positive delta H means that it is endothermic. Okay, the reaction increases in energy. The flip side is a exothermic reaction. In an exothermic reaction, energy is going to be released, so the energy of the products will be lower than that of the reactants. So the products will be less than the reactants in terms of energy. So when we subtract products minus reactants, we're going to get a negative delta H, and that makes sense. If it enters, it would be positive because it's going into the reaction. And if it exits, it'll be negative because it is leaving the reaction. Okay, so in order for this reaction to even start, we have to reach a point called the activated complex. And so the activated complex is this part of the reaction where the reactants are actually kind of smashed together. So in order for a reaction to begin, the reactants must have enough energy or speed to form the activated complex so that they can interact with each other. So let's say we had just a made-up compound XA plus YB, and it was going to become XB plus YA. That would be a double replacement reaction because the metals were switching places. But the activated complex would be this intermediate compound where XA and YB were close enough together that they could interact with each other. So the activated complex would be what we call XAYB together. Where does the activated complex occur? It always occurs at this hill of energy. Either endothermic or exothermic, you're always going to have this top part of the hill. And at the top part of the hill, we have the activated complex. And that's on both of my graphs. And the activated complex is where you have the intermediate form where the reactants are pushed together. The amount of energy it takes to get from the reactant up to the activated complex is what we call the activation energy. So the activation energy is the amount of energy needed to start the reaction. Some reactions happen very easily. They have a low amount of activation energy. Some reactions require a lot of input in order for the reaction to start. Okay, but the distance between the reactant and the top of the hill, or the activated complex, is what we call the amount of activation energy. And we'll talk a little bit more about a catalyst in just a second. Let's go ahead and look at some potential energy diagrams. So I've kind of redrawn the potential energy diagrams from your notes. And so you can see this is what you would see on the computer, but we're going to go through and talk through and kind of label everything. Make sure we understand what we need. Okay, so I can see, looking at this first graph, and go ahead and start and say, well, this is my reactants and this is my products. I know that my reactants have released energy to go to my products. So if my reactants have released energy, this must be an exothermic diagram. Okay, so the type of diagram, I know it's exothermic. My reactant energy, what's my reactant energy? Well, it's actually 45 kilojoules per mole. I can just look at that by reading it over. And my product energy is 30 kilojoules per mole. And I just did that by looking over and seeing what my product energy would be. Okay, so what's my activation energy? Well, remember, my activation energy is the energy it takes to get to the top of my hill, the top of my activated complex. So I'm starting at 45, and I have to go up to what looks like about 55. So to go from 45 to 55, my activation energy would be 10 kilojoules per mole, because it's the distance between here and here. So it's about 10 kilojoules per mole, or my activation energy. Okay, my delta H. Remember, my delta H is always going to be my products minus my reactants. So delta H equals products minus my reactants. So what was my product energy? My product energy was 30 kilojoules per mole. My reactant energy was 45. So 30 minus 45 would give me negative 15 as a delta H. That negative tells me that it is exothermic. So negative 15 kilojoules per mole would be my delta H. And again, this is reading left to right, reactants to products. And my activated complex was at 55. We said that was at the top of the hill, kilojoules per mole. So that's the amount of energy that they would be required in order to form the activated complex, or that intermediate form. Okay, so let's talk a little bit about forward reaction versus reverse reaction. A forward reaction is where we just read the graph left to right. Left to right. The reverse reaction is if we read it in the opposite direction. So it would be right to left. Okay, so the forward reaction would be that this would be my reactant and this would be my product. So 30 minus 45 would give me negative 15. But what if I actually reverse this reaction and I had the products in turn becoming reactants? So if I reverse the reaction, I'd have to read it in the opposite direction. I'd be going from 30 up to 45, which would actually be a positive 15 delta H. Because remember, reverse reaction, you're actually flipping your labels. So instead of thinking of this as being the product, it would now be the reactant. Instead of thinking of this as being the reactant, it would now be the product, because we'd be reading it from right to left. So 30 minus 45 would give me a positive 15. So my reverse reaction would be an endothermic reaction. So what's my forward activation energy? So again, remember, that's reading it left to right. So my forward activation energy is from here up to my activated complex, which we said was from 45 to 55, which was about 10 kilojoules per mole. So what's my reverse? Well, that would have to be from here up to the top. So from 30 up to 55 would actually be 25 kilojoules per mole. Remember, because remember, when we read the reverse, we read it from right to left, so it would have to be from here up to here, so that would be from 30 to 55, which would give me 25 kilojoules per mole. And now let's talk about a catalyst. Okay, so referring back to our notes, so what a catalyst is a helper. That's all a catalyst is. And what a catalyst does is it lowers the activation energy. And the way it lowers the activation energy is it helps those reactants form that activated complex, or that intermediate form. You'll learn later in chemistry and biochemistry about the way that the molecules catalysts hold molecules in a right position to make it easier to connect. But basically, we just need to know that it lowers the activation energy. It's not used up in the reaction. It's just a spectator. Remember, we talked about spectator ions when we were learning about single and double replacement reactions. So it's not used up. It's just kind of there, and it helps the reaction happen. It doesn't change the starting energy. It doesn't change the ending energy. What it changes is the amount of energy required to get somewhere. So what a catalyst will do is it'll come in and it'll lower the hill. So this would be the impact of a catalyst. And different catalysts are going to do different things. The concept that we just need to understand is that the catalyst lowers the activation energy, lowers the amount of energy required to reach the activated complex. We would now be able to reach the activated complex there. The delta H is going to stay the same, okay, because we're not changing the distance between my reactants and my products, or my delta H is not changing. The only thing that's changing is the amount of energy required to start the reaction. A catalyst lowers the activation energy and lowers the activated complex. Okay, so let's look at another example. We're going to kind of go through the same thing again. What type of reaction is it? Well, I can see that I increased in energy. Since I increased in energy, I must have an endothermic reaction. Let's go ahead and label my reactants and my products. Well, my reactants are my start, my products are my end. Okay, and then how much energy? So my reactant energy is 40 kilojoules per mole. My product energy is 60 kilojoules per mole. My activated complex here at the top looks like it's going to be about 65. So my activated complex is going to be 65 kilojoules per mole. All right, so what is my delta H of my forward reaction? Well, remember that's going to be products minus reactants. So delta H of the forward reaction is going to be 60 minus 40, which gives me a positive 20, which makes sense because positive should be endothermic. So positive 20 kilojoules per mole. Well, what about the reverse reaction? Delta H for the reverse reaction would be going in the opposite direction. So I would go from 60 down to 40. So 60 down to 40 would actually be a loss of 20. So my delta H, or my reverse reaction, would be the opposite, 40 minus 60, which would give me negative 20. So we can see that the forward and the reverse reactions are opposite of each other. So it would be negative 20 kilojoules per mole. So that's my reverse reaction. Let's talk about my activation energy. So my activation energy of my forward reaction, remember that's left to right, takes me, I'd have to go from 40 up to 65 is going to be my activation energy. So from 40 up to 65 would be 25 kilojoules per mole. From 40 up to 65. But for my reverse reaction, the activation energy of the reverse reaction, it would be from 60 up to 65. So that would only be 5 kilojoules per mole. And then lastly, what would happen if we added a catalyst? Remember, all a catalyst does is lowers the Hill. So doesn't change my starting or ending point, it just lowers the Hill. So a catalyst would lower the activation energy on both the forward and reverse reactions, but it would lower the activation energy. Okay, so let's take a second, let's look back at our notes, let's make sure that we can answer all of our questions. Do we know what the energy of a reaction is? It's the amount of energy either absorbed or released. We know that in an exothermic reaction, the reaction loses energy. In an endothermic reaction, the reaction gains energy. My next question is, how are endo and exothermic reactions different? Well, we kind of just talked about that. We said that exothermic is going to have a lower product value. Endothermic will have a higher product value. What must happen in order for the reaction to begin? We have to reach that activated complex, or that intermediate form where the reactants are smashed together so the reaction can start. And so we have to gain the energy to reach that. And that from the reactant up to the activated complex, again, is called our activation energy, the amount of energy required to start the reaction. And how does a catalyst impact the energy diagram? Catalyst lowers the activation energy. It makes it easier to reach the activated complex. So it's going to lower the Hill, but it does not change the reactant or product. We also talked about forward and reverse reactions. Forward is reading it left to right. Reverse is reading it right to left. So we're reading it in a backward form. Okay, one thing I just want to show you on your Regents table. So this is your Regents packet. And if you'll look for just a second with me at your Regents packet, we're going to look at table I. They may ask you, is a reaction endothermic or exothermic? And they would give you the reaction here. Well, we just have to look at the delta H. Remember, anytime the delta H is negative, it is exothermic because it lost this amount of energy. Anytime it is positive, it would be endothermic because it gained that amount of energy.